Yes, I'm very happy to have Mark Keane here today with us, and he'll be talking about augmenting the weather using counterfactuals to deal with dataset drift caused by climate change. Mark is a professor at the University College Dublin and has been in research since, at least it says here, the chair since 1998. His research interests are cognitive science, computational creativity, data analytics, and is it smart agriculture? And I have known Mark from the case-based reasoning community, and we have met over the past few years, and he has been given excellent talks on the topic. So I thought it would be nice to share his research with this community. So I hand it over to you, Mark.
Okay, so thanks very much, Kirsten. This picture hello, I should say hello from Dublin, Ireland, but this is a picture of your country. This is Svalbard, which was our last big family holiday before COVID hit. And our plan is to try and get back there if we can afterwards. But I'm sort of saying I wish I was there rather than here at the moment. As Kirsten said, my name is Mark Keane. I'm the chair of computer science at University College Dublin and have been that for a very long time. I'm also part of these two research centres, one on Insight, it's the Insight Data Analytics Centre, and the other is a precision agriculture centre called Vistamilk, which I'll mention some of the research we've done there in grass growth and dairy farming. This work, I should say, is really jointly done with one of my PhD students, Mohammed Temraz, and my co-colleague on the algorithmic stuff is Barry Smith. Okay, so I'm going to talk about data augmentation using counterfactual methods, which is a fairly new idea. I think there's only about 2 or 3 groups that have even mentioned it as something to do. But I hope it sort of potentially has a big future. I'll talk about some of the background and history in the use of counterfactuals, which is mainly in the XAI area where it's got really big in the last few years. And then I'll talk about some of the intuitions for why we feel using these methods from XAI may actually have some applicability in the data augmentation space. And then I'll talk about one sort of case study we did around this precision agriculture area, which is in predicting grass growth, and how we've tried to deal with the impact of climate disruption on future predictions, essentially from AI models. And then I'm going to talk very, very briefly about the wider sort of context for this work, where we show that this method actually generalizes quite well. And then finally, I'll end with a final slide with my best explanation for why I think this works. Okay, so I'm going to start with the history, if that's okay. And I don't know if people are aware of David Lewis, but there's a lot of people really like his work from logic and philosophy, where he produced one of the first sort of logical analysis of counterfactuals in the context of possible world semantics. And so his proposal was, the thing about a counterfactual is that it's the closest possible world in which an outcome is different. So imagine a situation where, for example, there's a terrible accident and you have a car crash on the way home, where you took a different route. And often in a lot of the psychological studies of this, people are asked, well, what would you have done, for a different outcome, or, if only such and such hadn't occurred. And people often say something like, well, if only, I'd taken the normal route home, I probably wouldn't have had the car crash, or maybe I wouldn't have had the car crash. So the idea with the counterfactual is that it's a very close situation to the situation that happened, but it's one in which the outcome changes because some feature of the situation has changed. I knew some people that worked with Kellogg in Princeton, and one of the funny things they said about him was that he actually believed that this was a description of reality. In other words, he believed those possible worlds really existed. The idea, too, has been studied very heavily in psychology. Danny Kahneman, the Nobel Prize winner, did some early work on it. And a colleague of mine who I've been collaborating with in the last few years, who happens to be my wife, has written a book on it several years ago, where people have looked at people's use of counterfactuals. They're often very important in emotions like regret, where people look back and say, if only I'd done something different in my life, then things would have been much better. But they also seem to be implicated importantly in causal thinking. So when people entertain counterfactuals, they seem to analyze a situation for its root causes. And that's very important because it means that it sort of elicits very active thinking about something. And in fact, very recent work done by a group in Stanford has shown that when people make predictions about things like billiard balls moving around a table and what will crash into each other, it shows that people seem to simulate implicitly counterfactual alternatives to the situation. Now, this is important for explainable AI because in explainable AI, we really want to give people automated explanations that cause them to think about what the model is doing and what's leading to the outcomes that a given model is showing. And so just to give you an idea of how counterfactuals have been used in XAI, imagine you have a system, and the classic one people talk about in this area is a loan application system. You could imagine that the AI, when it refuses your loan, gives you no explanation, so it just says go away. You could have a sort of factual explanation, which would be a traditional sort of thing that's done in case-based reasoning, where you say, look, you refused a loan because your profile is very like this other person and they were refused and that's why you refused. The counterfactual idea is sort of quite different to a factual explanation because it says something like, if you earned 5K more, then you would have gotten the loan. So again, as I was saying earlier, the important thing about it is that it indicates how the outcome would change if some other feature changed in the situation. So in other words, if my salary was slightly higher, I would get the loan. And people have focused on this as being important in XAI because it doesn't just tell people something, about the decision, but it sort of gives them a route to fix the decision or to reverse the decision. And so there's a whole new area now called algorithmic recourse, which studies this issue of how do you give people some option or avenue to change what has happened to them. Now, when you think about counterfactuals, there's about three main properties that people propose are important. In other words, important to making them work or important to making them good. The first is this notion of sparsity, which in a simple sense is just that when you have feature differences in the counterfactual, they should be few in number. So the examples I've given you have all been single feature differences, like an increase in your salary. Now, it would be less good as a counterfactual if I said something to you like, if your salary increased and you had a better credit rating and you applied for a lower loan, that sort of counterfactual is sort of not as good, if you like, as a much sparser one with fewer feature changes. The second idea in the analysis of counterfactuals is that they should be proximate. Now, what I mean by that is that, just as Lewis said, they should be the closest possible world. And this is what made counterfactual explanations sort of computationally interesting, because the issue is, how do you actually compute an explanation that's as close as possible to the situation you're in to help you explain a different outcome that could occur? In fact, some of the early work that was done, again, by another one of my colleagues, Paul Cunningham, in 2009, looked at this proposal and computed it essentially as nearest unlike neighbors. So the idea is that you go back into the data set, you try and find another data point that's really close to your situation, and then you use that as the counterfactual explanation. So these are the sort of the none solution. Now, the problem with that is of course, you're sort of limited by the data set, because you may not always find a nearest unlike neighbor, or you may not find a nearest unlike neighbor that's actually very close to the situation you're in, and therefore the explanation would suffer as a result of that. And this led to a very different approach, which has had huge impact in the last few years. It only came out in about 2017. It probably has several hundred citations now as a piece of work. And what it is trying to do is generate synthetic counterfactuals. So in other words, for any possible situation that people might enter into a loan system, you can produce a close counterfactual explanation for that. And what they did was used ideas actually from adversarial learning, where what they do is they generate a space of perturbations of the situation, the original situation. And then they do a gradient descent to find the situation that's closest to the current situation in which there's a different outcome, essentially. Now, this is an interesting method. It works relatively well, and it's sort of the baseline case for computing counterfactuals at present. However, the thing about it that I never liked was that it is blind perturbation. In other words, it's just perturbing features without looking at what those features might be. There's very few constraints in what's being done. So sometimes this method actually generates out of distribution items. So it generates invalid data points, essentially, and you really don't want them as explanations. The other aspect I didn't like about this method was that it doesn't go back to the data set at all. It doesn't perturb things with any knowledge of what has occurred before in the data set. And that's what led us to try and think of a new method that did that in a different way. Which I'll come to in a minute, just to give you the final property, which is important to counterfactuals, and that's plausibility. So it's not just a matter of changing a feature, but you need to change a feature that's going to be plausible to someone. In other words, something they can do something about. People often talk about this issue of actionability in it. So you really probably don't want to be giving people about counterfactuals that suggest that they need to change their marital status or their gender or where they live in order to get a loan, because it just seems too radical and implausible. So just to move on to our method, which is a case-based reasoning type of method, I guess we went back and we looked at that none type of solution, and we made one big change to it. In other words, rather than going back into the data set and trying to find a nearest unlike neighbor to the situation, we actually go back into the data set and we look for counterfactuals that already exist in the data set. So in other words, if you take any data set and you look at some decision boundary in it, you can find these close counterfactual relationships between data points. In other words, a data point on one side of the boundary and a data point on the other side of the boundary that are separated, as it were, by a small set of feature changes, or a single feature change even. So let me try and explain how this algorithm works in detail so you have a good sense of it. Imagine this is our situation where I've applied for a loan here, and I'm looking for a loan of 100,000. There's this profile of my income and stuff like that. And, you know, not surprisingly, it tells me that I'm not going to get the loan. So what we do in this method is we try and find what we call these native counterfactuals. So these are, as I say, existing pairs of data points that have a counterfactual relationship between them. And so in this data set, there might be such a pair such as X and P, and X in this case is Jim. Jim looks really like me. In fact, he's essentially identical. And when he applied for a loan, he didn't get it either. But he's counterfactually related to this other professor who had a bit more of an income and actually asked for a lower loan. And this is the counterfactual relationship here, because the counterfactual tells us that maybe if you had a higher income and if you asked for a lower loan, then the outcome would be different. And in other words, you would be granted the loan. So we can view this as a sort of piece of information which exists in the data set that maybe we can leverage to generate an explanation for this original case where I applied. So the second step in this method then is this one of sort of adapting that. So the first step is you find this nearest neighbor that's in a native counterfactual. So a nearest neighbor that's part of one of these counterfactual pairs. And then when you find that, you take this P case and you try and adapt it essentially to produce an explanation for the original situation. And so I look at P and I say, so what should I take from P to change the original X prime situation, which is my description? And of course, one of the things the native counterfactual gives you is what features should be changed. In other words, the indication is that it's the income feature and the loan feature that should be changed to get the explanation for the counterfactual alternative. And so in doing this, we can produce this P prime, which is a sort of parallel, an adaptive parallel to the original P. And it says something like, well, Mark, if your income was 70K now, and if you asked for a lower loan of 90, then you would possibly be granted the loan. And this, of course, is the explanatory counterfactual that this system would produce to say, this is the reason why you didn't get the loan, essentially. So if these features changed, then you would get the loan. Now, one of the things to keep in mind about this is that this is a synthetic data point, right? So this is a wholly new data point that wasn't in the data set before. It has come from a data point we've seen that did exist in a data set, but it's an adaptation or modification of it. Let me just give you a long vision view, if you like, of where all this sits. We've just looked at one example there. So here we have classic data set. We've two classes, a green circle class and an orange square class. And our query, which is the one about me, pings into view here. One of the things we do with this method, of course, is compute these native counterfactuals. So we look at the data set, we find these close pairings between data points on either side of the boundary, and we connect them up, and they're the ones we're going to leverage, as it were, to get our explanatory cases. So the steps, which I've described already, is you find this nearest neighbor to x prime, which is x. And obviously what comes along with x is p, and then you use that p to generate this new data point, which is going to be p prime. And of course, one of the things we're doing with p prime here is, it's based on the matching features in the original situation, x prime, and it's based on the values of the difference features. So those features which are different between x and p get carried over into p prime, and we generate this new data point. There's a statement here about classifying this too. Remember, one of the things that you have to do here is determine whether that generated data point really is on the right side of the decision boundary. So what you do in these methods is you present it back to the machine learning model to determine that that is the case. And of course, at the end of this situation, we now have a new counterfactual, but it's a counterfactual which exists between an original real situation and p prime, which is this new generated synthetic data point. So that's, if you like, the sort of XAI bit of this talk, and it sort of explains the method that we've developed to generate these counterfactual explanations. And in the XAI area, these explanations look okay. They seem to do well, and this particular method stacks reasonably well against a lot of the other competitors in the field, of which I should add there's nearly 100 different methods at present. But what about using it in data augmentation? And this was a sort of side idea which occurred to me when I started to look at this. So, in the XAI case, as I've been emphasizing, you start with some sort of query instance. And from this counterfactual method, you end up with a synthetic instance in this counterfactual class. And the idea occurred to me and my colleagues early on that maybe, those artificial data points that we're generating, which we're using for explanations, would also be useful in a data augmentation context. In other words, they would be useful data points that could improve the predictive, if you like, power or accuracy of a model if we started to generate them in a given context. So imagine a situation where you have something like this. So we have, again, the green circles and the orange squares. We have some native counterfactuals there. And what we're going to do is something like this. So we're going to apply, instead of just applying our counterfactual method to a query which arises, we apply it to all of the data points which are not part of existing native counterfactuals. And that enables us to generate a whole bunch of new data points, at least in one of the classes, which we add then to the data set. So why would we want to do this? Well, we want to do this to fix class imbalance, right? So I don't know if you're aware of it, but the class imbalance problem is a fairly big one in machine learning. It occurs naturally in some situations where you have data sets where one particular class, by definition, generates very few data points. So for example, if you think about fraudulent credit card transactions, by definition, most credit card transactions are not fraudulent. So you have loads of data points on that, and very few are fraudulent. And so you have much fewer data points. And of course, when you have a machine learning model dealing with an imbalanced data set, all sorts of problems can arise. So it's often, you can get sort of spurious accuracy levels. It's hard often to get a really good idea of the decision boundary between the classes because you have so few data points on one side of it. And of course, the other main area, I guess, where this hits is in deep learning methods where they need loads and loads of data points and they don't have enough of them. So they need some methods to generate additional data points that are plausible and useful. So in the class imbalance case, you have this majority green class and this minority orange class. And if you think about it, essentially, when you look at a lot of the methods used for data augmentation, what they set out to do is generate these artificial synthetic data points that will fill up the minority class. So now you end up with a balanced data set and therefore a machine learning model that works much better. And so this was the idea we tried to take into this particular application case, which we knew about in a separate area. So we had been building models of grass growth prediction. So you're going to have to bear with me now while I tell you about dairy farming and grass growth, which I must admit I really enjoyed learning over the last 3 or 4 years. So think about climate. You can see here that you were sort of roasted in July 2018. There was actually a European-wide drought. It hit Ireland very badly. Normally, we don't get very warm summers, and you can see Ireland is red, as is an awful lot of Norway. In fact, what happened in the summer of 2018 was we got this very hot summer. So if you look at this graph here of mean temperatures, over the last decade, the black line shows you the typical temperature that occurs in Ireland over the sort of year. And the green line is the temperature in 2018. You can see this huge spike, which occurs basically in July. But the other thing about this year was that it actually had a lot of weird weather. So we had a very cold spring. You can see that big dip down there in spring. And we also had a cold autumn as well. And that becomes important to what I'm going to talk about later on. Now, when you look at grass growth, this is the classic grass growth curve, it's called. It has this characteristic shape, which actually looks very like the graph you get for temperature, and it looks very like the graph you get for rainfall. And the reason is, of course, grass tends to grow on the basis of having sufficient heat and sufficient moisture. Generally, grass doesn't grow. You can see at the beginning of the year in winter, and at the end of the year when late autumn and winter kicks in. It peaks up around June, in fact, and then eases off. June, July are generally the peak months for grass production. And one of the things, of course, that happened in 2018 was that this characteristic curve was essentially destroyed. So the green dotted line here is 2019, which is a sort of normal year. The red line is the 5-year average, and the purple one is 2018. And one of the things you can see about grass growth here is it peaked up sort of as normal in June, but then it shot right down in July. And essentially what happened here is you had low moisture in the soil and you had very high solar radiation. And when that happens, grass gets burned. So this is when the fields turn brown, essentially. So what actually happened here for dairy farmers was that they had no feed for their animals. And there was a forage crisis where we actually ended up importing grass and stuff like that from other parts of Europe. So this had a huge impact at the time, and of course was not well predicted at all. Why is grass growth important? Well, in Ireland, we have, we basically have what's called a pasture-based system. What that means is that animals are not in sheds, but they're actually out in fields for most of the year eating grass. And it means essentially that if a farmer manages their grass growth accurately, they will actually, have more milk and they'll generate a higher profit. The other thing about this is that it's a much more sustainable way of managing a dairy sector, because if you manage to feed animals on grass, then you avoid using imported feeds like soybeans or corn or something like that. So it's like eating everything is grown locally and the animals are eating locally. And so our collaboration in this was with this national research body called Teagasc. They actually have a platform where they help farmers manage their grass on their farm. And this is the desktop version of this decision support system. It's called Pasture-Based Ireland. This is actually a model of a farm. So each bar is a field, or what they call a paddock. The width of the bar tells you something about the size of the field, and the height of the bar is telling you essentially the amount of grass that's in it in the next week or so. Grass, by the way, is measured in kilograms of something called dry matter per hectare. Dry matter is the grass is cut and then dried and weighed. And so the idea that what the farmer is trying to do here is keep those bars above this red line. If the bars fall beneath that red line, then it means that they don't have enough grass in the coming week for their herd. And it will mean, in fact, that they have to start buying supplements, as they call them, to replace that. So farmers are looking at this on a regular basis, and what the problem we had was to try and predict 1 week ahead. At present, this system doesn't actually do prediction. What it just says is assume that the growth rate is what you have now this week, and that will be the same next week. And so by being able to predict what next week will look like allows you to be more accurate in doing this grass management problem. So in the early days of this, we took a huge lot of data entries, and nearly 100,000 entries from different farms. They're very simple records, just saying the environmental sort of situation, temperature, rain, etc., in a given week, and the amount of grass growth that was occurring. And we built a K-nearest neighbor model. We called it Pasture-Based Ireland Case-Based User, PBI CBR, to predict 1 week ahead. And we managed to get quite good accuracy at this. And because it was a CBR system, we could explain the outcome of these predictions in a factual way rather than a counterfactual way. So in other words, we could say to a farmer, the reason why we're predicting this is that this looks like a week you encountered 2 years ago in spring when the temperature looked like this and the grass growth was this. And that was our form of explanation in that model. However, one of the things that happens with this model is, of course, it fails on climate change. It fails to deal with 2018. And indeed, if you look at an awful lot of machine learning models we currently have, one of the key problems which is recognized even in the hugely successful deep learning models is that they have a problem getting beyond their data sets, right? So, you know, this is especially a problem when the future is changing, right? So even when the future is fairly static, these models have a problem with that. And climate is a case in point. Like past climate, as we've seen, is not indicative of future climate. And of course, what this means is that the historical data you have, even when there's lots of it, becomes progressively less useful. And I like to think about this as a type of sort of concept drift. So I previously worked in text analytics. You know, there's this idea in text analytics when you're tracking a news story that the story changes over time. So if the story is about a murder, then, you know, there's all these murder concepts being mentioned initially, but then the police catch someone, there's a trial, you have a whole new set of concepts that come in. And one of the problems that people have with machine learning models that are trying to track news stories is that they can't easily track that concept drift. So something starts being described by certain features and ends up being described by a very different set of features. And I think climate change is like that. It's like we have a set of features which are prior temperatures and rain measurements and stuff like that, and that they're just not going to be indicative in future as the data set drifts, essentially. So the question is, how do we, if you like, try and solve this problem by maybe using a counterfactual method or an explanatory method? So we went back to our grass growth data and we did a number of things to it. The first thing we did was we started to define what we call climate disruptive events or outliers. So we tried to identify in the data set those descriptions of growth on a farm that were climate disruptive or unusual events. And we did that very simply in the end by just picking something that was like 2 standard deviations from the mean. And we separated them from normal. So in other words, we're generating, if you like, an artificial decision boundary. And then once we have that, then we can apply our counterfactual method to it to generate new data points on, if you like, the outlier side of that boundary, because that's the side of the boundary which is underrepresented. That's where the class imbalance is occurring. These unusual events are low in number, and so that class is not populated very well. And our hope was that by applying the counterfactual method to it, we could populate that class a lot more, and with these new data points, hopefully predict things a bit better. So just to give you a visual of this, I mean, this was our whole data set over a number of years. And the graph on the lower part of this slide shows you what happens when you separate out, this is temperature, the high and low outliers. So these are the the very cold events which have occurred, or the very warm events which occurred. And of course, the middle part, which has disappeared here, are all the normal ones which were there. And I've just put the boxes around these to show you, these are the periods in which we see some of these more extreme behaviors. In detail, each of these cases, as I said, are very similar. This is this is the record that you have. It's a record that just says the growth rate, the week of the year, the month of the year, the rain that occurred in that week, and the mean for that particular feature in a given year. And also temperature and solar radiation. And so the normals are on the left-hand side here, and then the outlier one is on the right-hand side. You can see here that the mean for solar radiation here was 1946. And in this particular week, it was 2959. So it was nearly 1,000 of this particular measure higher. And this is the sort of data which essentially we're handling. So pictorially, we have a situation that looks something like this. We've a class of normals, a class of outliers. We have a decision boundary between them, and we've separated them using the statistical measure of the standard deviations. Now, when we did this to the 70,000 or so data points we had, we ended up with a whole bunch of these outliers that were ones around rain, some of them were around temperature, and other ones were around solar radiation. And essentially what we're trying to do here, if you go back to our early pictures, is to take something like this. So the blue ones are the ones that are the normals, the outliers are the orange boxes. And what we're going to do is apply our counterfactual method to all of the, if you like, residual data points that are not part of native counterfactuals, and generate a whole bunch of artificial data points in the outlier space. So the first experiment we did on this was actually to go back to our original model and see were outlier data points that existed that we knew about being used. So we ran a version of the model, the original model, which is PBI CBR-O, against a version of it where we just took out all the outliers. And the whole point of doing that was to see whether the outliers were playing any sort of role in predicting a difficult year like 2018. The second experiment, which I'm going to briefly show you here, is that we did a number of tests to see which outliers were being used to explain which target situations. So in other words, we wanted to see whether when you encounter a climate outlier like 2018, whether the model is using historical outliers to deal with that. And that was, again, a test to see whether these particular cases or instances tended to be used. And these are the results of those two experiments. So the one at the top here shows that there was a performance improvement. This is mean absolute error. When the original data set was used relative to the data set with the outliers excluded from it. Now, this difference you can see is fairly small here. It's like 2.20 versus 2.35, but you have to remember that this is kilograms of dry matter per hectare. So over a particular farm, this can get to be an awful lot of grass. That could be quite important. The second table here shows you essentially very strong evidence that the model as it runs is really using past climate outliers to explain future climate outliers. So 88% of the test cases that you're looking at that are outliers are actually predicted on the basis of some use of a historical outlier case. And this was good news because it meant that if we could use our counterfactual method to generate artificial outliers, then the likelihood is we should impact the overall accuracy of the model in dealing with these climate disruptive situations. And this is what we did in our second experiment, where we then pitched 3 versions of this model against one another. So the middle one here, DICE, is another counterfactual method. It's one of these blind perturbation methods that I mentioned earlier. CFA is our method, the counterfactual augmentation method. And the other condition here is native CF. So this is a sort of extreme test in the sense that what we did is we took just the outlier cases from the historical data, and we looked at how well they dealt with 2018. So in other words, we've thrown all the normals away and we're testing the historical outliers that we have against 2018. And then what we're doing is we're using the artificial counterfactuals generated by DICE and CFA in parallel tests of this. And one of the things this is showing you is that essentially, the best performance is coming from CFA. So the counterfactuals generated by CFA look like they're good at dealing with these difficult climate disruptive parts of the year in 2018. And in fact, if you put these results alongside the original graph I showed you here, you can see the places where the counterfactual method is doing well are exactly those places where we got this weird weather. So it's the cold spring, the hot summer, and the cold autumn, which occurred in 2018. Okay, so all of that looked very positive. It seemed to us, obviously, a very important problem to be able to deal with. But of course, people could look at this and say, well, yeah, I mean, so what, you've done for climate, but what about all the other data sets which exist out there? Does it work for them as well? And I can't talk about this in detail to you because it's a very large set of studies, but I'm just going to show you one instance of this work that we did. But essentially what we're doing here is we're going back to the class imbalance problem on its own. And so we want to see whether we can solve the class imbalance problem using this counterfactual method. But now we're going to use lots of different machine learning models. We're going to use lots of different data sets to indicate its generality. And we're going to look at how well it does relative to a bunch of these other methods, which the main one of which is something called SMOTE. So very briefly about SMOTE. It's hugely used in this area. There's about 16,000 citations to it, and there's about 20 or 30 different variants of SMOTE. And what we did is we pitched them against the CFA method to see how well they did. One of the things you're varying here is that the amount of the class imbalance there is in a given data set. And also it's important to look at different models because the decision boundary will be different for different models. So you want to see that your method works with a lot of different methods. Just to give you a sense of what SMOTE does, very simply, it deals with class imbalance situations like this. So we've way more green circles than we have orange squares. And what it does is it sort of finds groupings in the minority class, and it extrapolates a new data point between a certain subset of points that it finds there. Now, the variants of SMOTE do a lot of different things, but one of the interesting things that emerges from a lot of the methods is this idea about looking at data points that are close to the decision boundary. Often there's noise there, but it also seems like if you use them to generate artificial data points, that they're a lot more likely to be good. And of course, one of the key things you'll realize about the counterfactual method is that it does exactly that, although it does it in a very different way from the other SMOTE methods which exist. So this is my summary of a whole bunch of data. There's many different experiments. It's just one measure. It's the F1 measure, which might not be the best, in fact, to represent what's good. But in general, the CFA method does very good in lots of these different methods. There's 4 classifiers here, linear regression and MLP. There's a k-nearest neighbor and a decision tree thing. I think it's actually not shown in this diagram. RF classifier. And I guess the different lines in this spider graphs here are the baseline, which is the blue one, CFA, which is the red one, which is generally on the outside, meaning that it's doing better. And there's 25 or so data sets being tested here. And of course, the simple message you can see in this is that it's doing way better than most of the other methods, which are, a lot of the main methods and variants of SMOTE that have been proposed to do this data augmentation problem. And I guess the thing we take from this is that it works quite well. But of course, the residual question is, well, why? When we did the climate stuff, it looked sort of a bit magical to us, and we actually hadn't worked out why it would work, if it did work. And this is my current sort of best explanation of why I think it works. If you go back to case-based reasoning, in case-based reasoning, they have this notion of an adaptation rule. So even though case-based reasoning generally works off cases, there were also in a number of systems a sort of high-level abstract rules. So you might have something, if you were doing, say, house price estimation, there might be an adaptation rule that you'd have in your system that would say something like, look, if you add a room to any house, it adds 10K to the price of the house. And the thing about those rules is that they were often used to sort of modify particular predictions being made. And if you think about them, what they do is they sort of fill a gap in the case base, because if you apply that rule to every case that you have, you could generate artificial data points that would be a new description, if you like, but one in which there's an extra room and there's a change in the price of that house. So you can think about adaptation rules as sort of potentially being rules that can generate synthetic data points. And our view is that these counterfactuals are exactly that, but they're a specific type of adaptation rule. They're telling you the feature differences which lead to class changes, essentially. And they're highly constrained. You know, we're only talking about changing one or two features, which means that they're very controlled in the perturbation that they're carrying out, unlike the sort of blind perturbation. And so the likelihood is that these are very plausible transformations. And so what we're doing, in a sense, is we're taking plausible transformations which have occurred historically, and we're adapting them to generate new data points which seem to generate plausible transformations for the future. Now, in one sense, we're still populating, I guess, the climate case in a slightly blind way. But the point is, because we're doing it in this very constrained way, it looks like we're generating meaningful data points. And that's why we believe that the method works so well. Thank you.
Just the slide that you mentioned just before, one of the points of creating counterfactuals that are kind of realistic. I'm wondering whether, you know, some of the attributes in cases or in samples are probably movable and others are not. For example, if you go back to your loan example, it's hard to get a higher salary, right? But asking for a lower loan is feasible, so that you can include this knowledge when generating counterfactuals to create some that are actually feasible for the user.
Yeah. So, and you know, we haven't done a sort of analysis on this in detail, but my sense is that, remember, because we're working off counterfactual relationships which have occurred historically, right? I think that's telling you that, you know, this is a meaningful relationship that has occurred in the past, right? So what I'm saying is that I think those implausible ones will not be found, as it were, right? Because they won't have been things that occurred much in the past, right? Now, for example, if there's a bias there, you'll probably see that bias, for example, which would make that very plausible. And remember, there's a competition going on here between nearest neighbors, between lots of different counterfactual alternatives that are there. And one of them is being picked because it's the closest in some way. So there might be loads of other ones like that that are implausible, that are actually being pushed out because they are implausible or because they don't occur even. That's the other option. You know? Now, as I say, we haven't tested that, but one of the things we have tested is the closeness of the feature values to the original situation. And one of the things you find with our method is that the things that are generated are much closer than other models produce. So we believe that they're really in a zone of sort of plausible changes to the features. But we haven't tested specifically whether it might generate things that are, you know, those sort of implausible, non-actionable things. But again, I have a great belief in the data set, you know, like the data sets have information in them. And, you know, that's why I feel that that should fall out of the method, you know, in the grand scheme of things. But we haven't tested it.
Just a quick follow-up on those. Of course, the one thing is to kind of be close, but when you think about creativity or, you know, finding something that is novel, I guess you want to try to get out of this closeness to find something that that is not so foreseen. Do you have any thoughts on this?
Yeah, that's a good question. I mean, you know that, like, originally I was someone who studied analogical problem solving and analogical methods before I came to CBR. I haven't actually thought about that as a solution. I guess in creativity, people find that analogies sometimes work quite well. But of course, the whole thing about analogies is that they tend not to operate off the superficial features. So they would not be nearest neighbors in. Yeah, exactly, but of course, exactly. Yeah. But what you could define, and that's what an analogy does, is a different similarity metric for your nearest neighbors, which is based maybe on relational information rather than on attribute, sort of superficial attributes, as it were, which is what analogy tries to do. And in doing that, if you did that successfully, whatever the definition of a relation might be, you would have a person try and find like analogical cover. Now, of course, one of the things that the analogy literature shows you is that these things line up together a lot of the time. So something that has the same surface features often has the same deep structure in terms of its analogical relations.
Yeah, nice talk. Thank you very much. I was wondering about this Lewis, the philosopher, and also Judea Pearl. They really emphasize the connection between counterfactuals and causality. Yeah. Whereas you didn't emphasize it, at least not quite as much. So I'm wondering, are you proposing a sort of alternative perspective on counterfactuals that puts less emphasis on causality, or are you saying that you sort of added CBR or case-based reasoning as an additional thing into the mix of
that's a good question.
In addition to causality, what's your perspective on those things?
Yeah, I mean, so Pearl's stuff is very different, right? So he's modeling a network essentially, and then he's talking about this sort of the impact that counterfactuals have on the causal analysis, if you like, of that network. So it's a very different approach to doing things. I guess we haven't sort of moved to make any great claims about whether we're capturing causality with this method or not. My perspective coming from cognitive science is really around, how do people understand these counterfactuals? I believe that counterfactuals, as the research has shown, elicit causal thinking in people. And that's the interesting thing for me. It's interesting because it means that if you show someone a counterfactual in an explanation in an XAI context, you can be sort of guaranteed that they're going to reflect seriously on it. There's a lot of information we could give people in explanations that they'll just look at and go, or that will have no impact on how they think about the situation. And so for me, the causal dimension, which I'm interested in, is this psychological impact of it. So I wouldn't make great claims in AI as to what its implications might be for determining causality. And I guess in a sense that goes back to Kirsten's question, can we be assured that, this method will find, really deep sort of featural relations, that featural differences that are causally impactful in a way, is sort of like those ones would be the really plausible ones, I would imagine. And my feeling on that is, like, I'd say I don't know, and it's an empirical issue, but I also have problems, and I may be wrong in this, about I'm sort of infected by the philosophical view that we don't really know what causality is, and I'm not convinced that, like, for example, deep learning models actually discover causality. So I do like Pearl's analysis where he talks about these hierarchy of analyses, that I believe that deep learning models are working at a sort of associative level. I think our case-based reasoning model is doing something like that, but there's higher levels where you have these reflective steps, as it were, which are very different in the way they work. I don't know if that answers your question.
Yeah, that was definitely very interesting discussion. And I think is there time for one more question from me, Kirsten?
Yeah, sure.
I have one more, but go ahead first, Olivia.
Yeah, the second one was about the which features or which element of a case or a situation. It seems to be that are, is good. You spoke about sparsity as one requirement, one the desired thing, and related to that, it's it occurred to me that what is good as a counterfactual case or explanation may depend a lot on the setting or the goal of your system, if you will. I was thinking about for a historian, they may be willing to go back to hundreds or thousands of years in their counterfactual explorations, whereas for you and me, we may not be interested in going so far back if we want to, when we're applying for a mortgage or when we were thinking about what would have happened if I had done X, Y, and Z instead, or just X for that matter. So what are your thoughts about that?
Yeah, your intuition is exactly right. There's a whole swathe of counterfactual methods that really emphasize aspects of features, right? So, one of the things that Kahneman originally looked at in this area in psychology was the idea of mutability and unmutable features. So certain features can be changed and other features can't. Like I can't reverse my age. I can't. I can't. If someone tells me I have to be 10 years younger, I can't do that. And then within the mutable features, people have pointed out these things like actionable. The idea of actionability means, can I actually act on it? Like if you tell someone who's on the basic income to get, to earn another 10K, then it's not actionable. But if I'm earning 100K a year or 200K a year, then I could probably do that, I could find that sort of money. And that's going to be very context dependent and very relative, it seems to me. And then other people, to go back to your other question, have brought in causal models as well, because what they do is they show that a causal model constrains the features, and a causal model will tell you something about which features you really need to change or not change, right? Now again, I have a problem with that because I lived through the original classic AI, and I got over trying to build causal models. So when people start to tell me that I can make my counterfactual method work by putting a causal model in, I just sort of say, so what, But you're right in that, I guess when you talk about different people, looking at different features or finding different features differentially important or over different time periods, I think what you're sort of saying is that they come to it with a different causal model, So, and it seems to me that there is a sort of great relativity in this in terms of what counterfactuals will be actually good for some people versus other people or something like that. And it's not wholly clear to me that we have a solution to all of those things, which is why, I hope it's going to fall out of the data set rather than that I have to start building, particular methods to constrain features or to mark ones as being unmutable and other ones as mutable, or ones as actionable and not actionable, or something like that.
So Anders Löland is asking, first he's saying, thanks for an interesting talk. And then the question is, counterfactuals give us alternative outcomes, which means that they investigate only one side of the decision boundary. So have you considered almost counterfactuals? That is to investigate the decision boundary better.
Yeah, I think maybe what you're referring to is we've done a whole bunch of other work. We have a paper earlier this year in AAAI on what we call semi-factuals. And they were, again, looked at in psychology, but hadn't really been looked at in AI at all. And what semi-factuals are, if you like, they're counterfactuals, but on the same side of the decision boundary as the original query. And to give you a concrete example of it, it's like, imagine you tell the farmer, if you used 2 sacks more of fertilizer on your field, you would have got a much higher growth rate, to what you got. The semi-factual will say something like, even if you used 2 sacks more, it would make no difference. You would still get the same growth rate, right? When we started to look at this, people said, well, who would use this? But it looks like it's actually practically very important, because a semi-factual tells you something about the headroom in the feature. It says, you can vary this feature to a certain level, and it still won't make any difference to the outcome. I don't know if that's what you're referring to, but that's what it sounds like to me. And we started to look at them in a bit more detail. But one of the things we find in some other methods we have for this is that semi-factuals, you can compute them as a side effect of computing the counterfactual. It's like the point in the decision space just before you cross the decision boundary. So it's still very, very close to the original situation, but it's not over the boundary yet, you know. And sometimes it's very important to know that, you know. So you might be telling someone, like, even if you know, got 10K more, it's not going to make a difference, you know. So don't even start thinking about buying a house, you know.
So I think I would like to thank you, Mark, for your excellent talk. It was fun as always to listen and to share what you have been up to. And I think I'll be handing over to Trym.
So I just wanted to show you this picture here just to annoy you, right? So this is, you know, one of these 5 Viking ships that were found in Roskilde, I think it was. So one of them was built in Dublin in 11 something. But the really interesting thing is that this is a copy of it. But the main mast was from a tree from the middle of the Wicklow Mountains in a place called Glendalough. Now, it's really hard to get to Glendalough, like now, right? There's no river into it, and there's a really windy road, and it's about 30 kilometers sea. So it also basically, it's an oak mast. It was a single tree essentially that was used for the original mast. So it's, as I say, Irish innovation, you know, by Vikings.
And then it seems to be quite some technology in the end, right? This white thing, I guess, it indicates that it's not a boat from the Viking Age.
Yeah, that's true. Anyway.
Very impressive. Thanks a lot for the talk, Mark. Very interesting. And thanks a lot to everyone who joined. We are on time. You had a hard stop at 2:00, Mark. So you'll be in time for that agreement. So thanks again for the talk. And I think this concludes the webinar series for this year. So let me also say, Merry Christmas to everyone, and join back next year. So thanks.
Thank you, and I'm really sorry I couldn't get to be with you. So maybe another
next time. Next time.
Yeah.
Perfect.
Okay.
Thanks everyone.
Cheerio, guys. Bye bye.
Yeah. Bye.